Okay, so now we're ready to continue on. This is going to be looking at example number 3. So example number 3, what we have is, and I highlighted this or kind of colored it in so that we could see that this is a single link. It's just shaped like a triangle, okay? But it is going to rotate around what would be our fixed center of point A. So in this example, it says the link above, so link number 2 above, rotates at 15 RPMs, revolutions per minute, clockwise. Okay, so it's going to go around like this. Determine the following. Okay. So what I want to do is I want to just kind of introduce this to start off with, and then I'm going to give you a little chance to, fill in as much as you can below, and then we'll revisit and we'll come back and we'll kind of do it together. So first of all, from our problem, it's telling us that this whole link rotates at 15 RPMs. So we want to show that's its rotational speed. We want to show that arc pointed clockwise, okay? And we're going to call that W2. Okay, that's our angular velocity of link number 2, and that's equal to 15 RPMs, right? Now, this link number 2 has a perimeter of A, B, and C. A is going to be a fixed point. It's not going to move. It's just going to rotate about that fixed center. But B is out here 4 inches away. So this would, this would be the radius, the distance from the center of rotation to point B. That would be 4 inches. C also has a radius of 2.5 inches, okay, out over here, and also lies on link number 2. Now, the equations to kind of figure these items out down here are going to have this relationship, as we know, of one of 2 equations. It's really the same equation, but rearranged. On our first page, we have this relationship of straight line velocity is going to be equal to angular velocity times the radius. So I'm just going to put that up here as a reference. So V is equal to W times R. And we can also rearrange that to solve for W is equal to V over R. Okay, so it's really the same equation, just rearranged. Okay. Now, as you look here, remember, okay, W is going to be radians per second in and out of the equation. Okay, so it said W2, the angular velocity of link number 2 is 15 RPMs, but remember, you can't use that in the equation, all right? You have to convert it to radians per second before you could put it in here, all right? So with that as an introduction, what I want you to do is find out how many of these values down here you can fill in. Okay, so the angular velocity of point A, angular velocity of point B, point C, link 1, link 2, and then the straight line velocities of the items seen here. Okay, in some cases, you might be able to directly put it in. In others, based on the information you have from the problem, in other cases, you might have to do a little calculating. So I'm going to give you like 3 minutes to kind of fill in as much as you can. And then what we will do is we will go over everything together after you get a little time to work. So I'm going to just pause the recording and then we will be back. Okay, so now let's take a peek at our application here, our example 3. As we stated earlier, we're going to use this relationship of the straight line velocity with the angular velocity and the radius. And whenever we're in and out of this equation, it's going to, the W is going to be equal to RP or to radians per second. But when we report out or when it's given to us, it's going to be in RPM. So at times we're going to have to do a little converting. So the problem told us that this member is going to be, or this link number 2 is going to be rotating at 15 revolutions per minute. And it wanted us to determine the following down here. So the first thing is, what is angular velocity of point A? If we look here, point A is at the center of the rotation of link number 2. It's where it actually attaches to the frame. So if we look at point A, it's not moving, right? So what would its angular velocity be? It would be 0, exactly. So this is going to be 0. And you could say 0 RPMs if you wanted, but 0 is 0, right? So that's going to be 0. When we look at point B is on link 2. And if you remember, all the points on a link have the same angular velocity. So what would the angular velocity, the W of point B be? 15 RPMs. And we would leave it in RPMs because we're reporting it out, if you would, okay? So this would be 15 RPMs for point B. That same logic for point C. What would the W of C be? Angular velocity of C. 15 RPMs. Excellent. Okay. So any questions about those three yet? The next one is the angular velocity of link number 1. Link number 1 is the frame. So what's the angular velocity of the frame? Should be 0, right? Yep, we always know that the frame is not moving. So W1 is going to be 0. What about W2? What is the angular velocity of link number 2? Steve says it's 15. Anybody else agree? We got nods. Yep. Okay, 15 RPMs. Excellent. Okay, so angular velocities. Do those all make sense to everybody? Any questions on those? Now we're going to move into, so those didn't require any calculations, right? But now we're going to move into straight line velocities, and we are going to use this relationship up here, okay? So the first one is we want to know what the straight line velocity is of point A. Now this is going to be a question for anybody who hasn't answered a question yet, okay? So velocity of A. Who wants to take that one? David. It's 0. Now, why do you think it's 0? You are correct. Exactly. Point A is part of the frame, right? It's the center of rotation. So it is not moving in a straight line at all, right? Yep. So it is at rest. So VA is 0. Excellent. All right. Our next one is going to be the velocity of point B. The velocity of point B, straight line velocity, is out here. Now, we want to remember that straight line velocity, I didn't ask you guys to do this, but I'm going to draw it on here. Straight line velocity is going to be represented by a vector. Okay, that vector is going to point in the direction of rotation and be perpendicular to the radius back to its center. Okay, so B is right here. It's on this line right here, this 4-inch line. So we would draw the velocity of B, if you would, perpendicular to that radius, right? In the direction of rotation. Okay, so that means it would be pointing down and to the right. And this would be velocity, make sure it doesn't look like an R, velocity of B. Okay, so that's the direction that we would show the straight line velocity vector for VB. Okay, now, does anybody get the answer for VB? Ryan, what'd you get? 6.28, and that would be inches per second. Okay, all right. So that's an answer. Let's make sure that we know how to get that, right? So we're going to use this equation right here, right? And I'm gonna kind of put this up here because I'm going to need a little bit of room. So I'm going to say velocity of B is going to be equal to W2 times RB, right? W2 times RB. Now, my radius of B is going to be the distance from the center of rotation out to where B is, right? So this is going to be my RB, correct? So that's going to go right here. So 4 inches is going to go right there. But as we had stated earlier, we can't use the RPMs in this equation, right? So we need to convert the 15 RPMs into radians per second, right? Let's do that right here. So we're going to actually, Yeah, I'll do it here. I'll do it right here. I'll have to write small. So W2 is going to be equal to 15 revolutions per minute, right? And I know that one revolution is 2 pi radians. I'm going to sneak it in here. 1 minute is equal to 60 seconds. You guys see that? I'll zoom in so you can see it. So this is revolutions, cancel, minutes, cancel, radians per second. So 15 times 2 times pi divided by 60. What do I get for W2 in radians per second? David? 1.57, and that's going to be radians per second. Anybody else get that same number? It sounds correct. Yeah. Okay. So now this is the value we're going to use down here, right? So this is going to be equal to 1.57 radians per second times 4 inches, right? Okay. So our VB, does that come out to 6.28? Yeah. 6.28, and then because radians in here multiplies by inches, it just goes to inches per second. So our velocity at B is indeed 6.28 inches per second. Awesome. These are fun, aren't they? David's having fun, smiling back there. You're welcome for coming to Basic Mechanisms today. All right, excellent. Yep, 6.28. Thank you, Garrett. All right, I like it. Velocity at C. Velocity at C, it's going to be that same format, right? So velocity at C. Didn't ask you to, but I'm going to draw the vector for the velocity at C. I've got some interference here. This is going to be velocity at C, right? My vector is going to be perpendicular to the radius back to the center of rotation, which is 2.5, which will be my radius at C, right? And it's going to be pointing in the direction of rotation. So if we're going clockwise here, our velocity of C is going to go up and to the right at this point in time. So to calculate velocity of C, right? What is my number here? Anybody get a velocity for C? Did you get that far? Oh, I'm not worried about how to calculate. What's your final answer? David, what'd you get?
3.925.
3.925, and that would be inches per second, right? And let's just, now we're ready to determine its magnitude. So velocity at C is going to be equal to W2 times RC, right? And Lars, now let me know what I'm going to put in.
That would be 1.57 radians per second. It's 2.5.
Absolutely. Yes. So we're going to take that W. It's the radians per second, the 1.57 radians per second. Don't put 15 RPMs in there. And then it's going to be multiplied by the 2.5 radius. So velocity at C, does that come out to be 3.925? Yeah, looks like it would. That's going to be inches per second. The radians magically disappear. You won't ever forget it again. Seriously. Get your money's worth today. Okay. 3.925. Thank you, Aiden. All right. So any questions on velocity of B, velocity of C on link number 2 there? Okay. Again, you weren't required to put those in, but it's good to show them because you will be doing it on a regular basis. All right. Straight line velocity of link number 1. What's that? 0, right? And then straight line velocity of link number 2. It's not 0 because it's moving. okay? But it's non-applicable because when we look at an entire link, it only has angular velocity, okay? So we're going to put NA, non-applicable. But points on a link, B, C, A, or maybe in between points, those would have a straight line velocity component, not the link itself. The link is rotating. It only has angular velocity, okay? All right. So as we have these values here, are there any questions on any of the answers or the calculations that we did here? Okay. Awesome. Cool. So hopefully on some level, it was a review, okay? Meaning you probably, I'm certain you went over these relationships in physics, might have been a little while. Just make sure that we're all on the same page. So I'm sure it's something that you've seen before, but hopefully it was a good review of that. So today, I'm going to stop there in our handout because I've got to save something for the next time. Otherwise, you guys won't come back, right? You have something to look forward to. So we're going to stop there content-wise. But before I go, what I do want to do is I want to look at our assignment and show you that for what we've accomplished today, there are some problems you can get started on in assignment number 4. So as we look here, I'm going to just, before I go to assignment 4, the practice problems, we already did example 6.1, and then we will be finishing up the handout the next time we're together to round out our practice problems. So nothing to hand in just yet for practice problems. But then assignment 4, you will be able to work on the first 3, 6, about 8 problems here, okay, based on what we went over today. So through 6.12. The remaining problems we'll be going over the next time we're together, okay? So let's look in the back of our book, starting on page 161. This is at the end of the chapter, okay? And what we'll do is we'll just kind of look at the problems here at the beginning so that you can see, get a little bit of direction on what it's asking for. So our first problem is 6.1. Says a package is moved at a constant rate from one end of a 25-foot horizontal conveyor to the other end in 15 seconds. Determine the linear speed of that conveyor belt. This is just like example 6.1. Okay, so your relationship is going to be velocity is equal to distance over time. Okay, so using that example 6.1 is how you would set that one up. The next one is a hydraulic cylinder extends at a constant rate of 2 feet per minute. Determine the time required to traverse the entire stroke of 15 inches. So first off, you're going to notice that it gives you the velocity. So this is the velocity of that cylinder, okay? And it's giving you in feet per minute. But they want you to report out, or they're giving you the stroke. How long will it take to go 15 inches? Okay, so what you need to do is you need to convert your 2 feet per minute to inches per second. Okay, and then what you're going to do is you're going to solve for time in this equation. Okay, you've got the distance, you've got the velocity once you do the converting, and then you'll solve for the time. Does that make sense to everybody? And again, remember, write out in variable form, add your units, do the cancellations to be sure that you end up with the appropriate units in the end. So here they want to determine the time. You should end up with seconds, okay, as your final units. For the next one here, determine the average speed in miles per hour of an athlete who runs a 4-minute mile. So they're running 1 mile in 4 minutes. This is a conversion. You want to change that to miles per hour. That's all. Okay, so it's a direct conversion. Do it in the ratio format, up, down, not in a slash and not in a multiply by. Okay, don't do any of those to me. I want to see it in step format. The next one, determine the average speed in miles per hour of an athlete who can do a 100-meter dash in 10 seconds. That's another conversion. You're going 100 meters in 10 seconds. Now you've got to know, though, this is meters. You've got to get to miles. Okay, so that you'll have to do a conversion for. All right, again, ratio method, though. Ratio method. The next one, a gear is uniformly rotates 270 degrees clockwise in 2 seconds, okay? Determine the angular velocity in RPMs and radians per second. This is another conversion. You're going to say 270 degrees in 2 seconds on the bottom per 2 seconds. And then 1 revolution is how many degrees? 360, right? So then you're going to 360 degrees in 1 revolution, and then you're going to multiply across, divide by the bottom, and then that's in per minute, and then you've got per second, radians per second. Okay. Those are easy peasy, aren't they? Okay. Determine the angular velocity in RPMs of the second, minute, and hour hand on a clock. Well, that's kind of fun. So you want to calculate in RPMs what each one of those are. One of them is 1 RPM. Okay. All right. So those are kind of the first introductory ones. Okay. And those are writing out. There really isn't really a diagram unless you want to add that for those. Okay. The next one you have here is number 11. Okay. Number 11, it says you have a drive roller on a conveyor that is shown in figure P611. So that is up here, right here. Okay. They want you to determine the angular velocity, which is W, of the roller when the belt operates at 10 feet per minute. Okay. So if we look at this, now this is the conveyor. Its belt is going to the left. Okay. Now, if we look at this in this sense, okay, I'm going to kind of break it down like we see it. This is problem 611. Okay. So if I look at the center of rotation here, okay, here's my frame, and I look straight up. This is just the radius of that roller, okay, to the top of the belt, okay, where the belt is on that roller. So this would be the roller going around. Remember how in our kinematic diagrams we didn't show a circle, we just showed a radius. So this is the radius of that roller, and the velocity of that belt is going to the left, right? So this would be the velocity of that belt. Now, as we look, this roller is going around in a counterclockwise direction, because if the straight line velocity of that conveyor belt is going to the left, this is going to be the W, right? Now, this is the frame number 1. This is number 2, link number 2, which is going to be that roller or the radius of that roller. So this is going to be W2. A would be the center of rotation, right? Kind of our standard way that we label. And this would be point B. So this would be the velocity of B. This is also the straight line velocity of that conveyor belt, which it tells us in the problem is 10 feet per minute. So this is equal to 10 feet per minute, right? Oopsie, I'm so sorry. 10 feet per minute. So what you want to find is W2. And you need to report it in RPMs, the final answer in RPMs. Now, additionally, I think they tell you what the size of that roller is, right? Oh, it's a 16-inch diameter. So this radius right here, RB, is equal to 8 inches, half of that, right? Sorry, I keep going high on that. So the radius from the center of rotation from A to B is 8 inches, okay? So you should have everything you need. That relationship of W is equal to VR is what you're going to use to solve for W2. Okay. Any questions on that one? All right. Then number 12 is using that same roller diagram, but this time they want you to determine the linear speed of the belt, which is going to be your velocity, when the roller operates at 30 RPM counterclockwise. Okay. All right. So this time in 12, you don't know what you need to solve for VB given W. Okay. So it's a little bit different problem. Does that make sense? Okay. But you're using the same layout, if you would, here in the sizes, physical sizes. Do you want me to kind of write out problem 12, or do you feel confident with the changes? No? Okay. I'll let you do it. We'll let you kind of make that leap. Okay. So right now, those are the problems that you would be ready to work on based on what we had gone over today. The next time we get together, like I said, we'll finish up the rest and then you'll have more to do. We'll build on that. Okay. So any questions before I let you go? Okay. So then what I'll do is I'm going to stop our recording